Hi everyone, thank you for coming to our seminar series. Today we have Dr. Shima Parsa from the physics department joining us, and I will quickly introduce Dr. Shima and then we'll leave the floor directly to her. So Dr. Shima is a assistant professor at the physics department at RIT and experimental matter physicist. Her research focus more on exploring dynamics and complex fluid, focusing on multi-scale. And some of you have already met with her during the seminar course. She recently received the NSF Career Award, and today she's joining us to share her research. And please join me welcoming Dr. Shima. Please.
Thank you. Thank you, Dima, and thank you for having me. So as Dima mentioned, I'm a professor of physics, assistant professor of physics. My lab is downstairs and my office is upstairs. So I'm always in this building and I have been in this building for the past 6 years. So the beautiful video you're seeing is from Adobe Stock videos, because to make that video, you really cannot do that with scientific cameras. Scientific cameras are just black and white. It just gives you gray. But this video captures the essence of complexity of the systems that we study. So droplets deform. They usually have a density difference with the surroundings, so they might go up, go down. If you have a lot of them, they interact with each other. And although it sounds very simple and it's like an everyday problem, solving it numerically is almost impossible. So that's where experiments come to play. And it's important to understand complex systems like emulsions or droplets or foams because they're everywhere. And if you want to scale up your operation, you need to be able to predict how things are going to behave. If you want to get mayo out of ketchup out of a bottle and it doesn't come out, that's shear thickening. You have to shear thinning. You have to shear it so it can start flowing. When you're whipping eggs for a cake or when you're making espresso, use foam, sunscreen, or you're trying to get that fancy expensive shampoo to the strands of your hair so the material actually delivered to your hair, you really need to get these emulsions to move around and do things for you. So they appear in a lot of applications, and it's important to understand them and be able to predict and actually manipulate them. But as a physicist, we usually address a different kind of question. We have a highly damped system, it's highly interconnected, and we're going to create small perturbations. And we want to understand how these small perturbations will impact the larger scale transport. So in this video, you're looking at two droplets trapped in a very simple array of posts. And the first one, which is on the left side, has been there for quite some time. As soon as the second one comes in, it disturbs the flow around it, which we cannot see because it's transparent, and creates enough fluctuation in the flow around it that it mobilizes the other one. And once that first droplet is mobilized, it's just continue going. So you wouldn't know that before. Well, we wouldn't know that for the entire 2 hours we were sitting and watching these droplets in this experiment, when it's going to happen and how close that droplet should be or how much things you need to have around to mobilize that single droplet. So from a physics standpoint, this is not an unknown problem. You have to balance forces, and it's very classical. You have a droplet, it's trapped between two posts. There is a capillary pressure inside the droplet. It's the pressure that holds this droplet together because the surface of the droplet has an interfacial tension with the surrounding. These are different molecules from the surrounding fluid, and they hate each other, so they want to stick together, and they remain as a droplet. Also, we're going to have to deform this droplet because this is slightly larger than the pore that's trapped in, so you have to elongate it, and that shows up in the parameter G. Interfacial tension is our denominator, gamma. It has a radius. The radius of the droplet is very important. If the radius is very large, the pressure is small. If the radius is very small, the pressure is very large. And we are pushing it with another fluid. So this is the counter force. And the fluid we're pushing it with has a viscosity. That would be the eta in this equation. So once everything is in balance, we can define a capillary number, which is very common in most of fluid mechanics. You have a non-dimensional number that defines your equilibrium, the balance of all forces. In this case, we are balancing the deformation of the droplet and capillary pressure with the viscous pressure from the fluid, and that gives us a capillary number. Once you have more forces in the numerator, it means that your droplet should be mobilized. So for a single droplet, there is like 50 years of research that can explain this problem very nicely. But as soon as you put them in a porous medium and you have all these pores connected to each other, you have an entirely different problem. It's a statistical problem. And it's kind of challenging to study that in 3D. So this is a problem that has been really of interest in oil industry. They have oil in the reservoir rock and they have to push water in, and water has to push the oil out. So we get a lot of oil out of it. But we can't see under the ground, obviously. And when they want to do experiments, they take a core sample, which is a piece of rock from the reservoir, and they try to do experiments on this piece of rock, and still you can see inside of it. So this example of this paper shows we're going to make emulsions. So we have water and oil or emulsion, and we inject them into the core sample. We kind of know what size the emulsions are when they go in. And what we can measure is like the pressure change across the sample and what size emulsions come out. So they show us at low and high capillary number, which means at low and high pressure, what kind of distribution of droplets you get. They're not very different. So the blue and the red curves don't really look any different. So we get droplets of equal sizes. It doesn't matter if we push hard or if we don't push hard on this. We get droplets of the same sizes. The thing is that we don't see anything at the microscale. So we don't know if these droplets that were generated, they go in and they break up into different droplets, or maybe they coalesce, or the large ones come out, the small ones get in, or some of the small ones become large. So there are a lot of questions that we cannot answer just from looking at what goes in and what comes out. One method of looking at things under that happen in small scale is looking at fluids that have the same index of refraction. So the video up there is actually my data. We are looking at oil, which is the black snaky thing that's going between some other black circles. Those are glass beads. So this is a packing of glass beads that represent what would be a rock. So inside the rock, we have a lot of grains. They're packed together and we have pores between them. Glass beads are the poor man's way of representing a rock that you can see inside of it. We have water, which you cannot see, and it's kind of light gray. And we have an oil that is not fluorescent. That's why it's so black. And we're flowing water from top to bottom. And if you follow those droplets, they go between these pores and they move through the sample, right to left, left to right. It's going to be one of those. And although we can see that using a fancy confocal microscope, still these droplets go out of plane. And then tracking them out of plane is extremely hard with a microscope like this, because this microscope has to, we talked about this actually a few hours ago with the first year students, has to move an objective. And this objective is not light. So it's really limited how fast it can go and how stable it can go. So you can see like a few hundred micron over a time span that is not the time span that these droplets go through. And you cannot really slow down these dynamics because mobilization is actually a very, very intermittent dynamic. It's going to be fast and then it's going to get stuck and then and it's going to be slow. So you can't really predict any of these. So this is one of the challenges of studying emulsions in porous media. So many people solve that problem by reducing one of the dimensions, and they say we're going to look at it in 2D. So this paper came out a few years ago. Now it's like 5 years. Very, very interesting experiment where they have decided, I'm going to walk away, and the people who on Zoom won't see me. They decided to design a porous medium instead of having those posts to have dips on this surface, and that's the porous medium. And this is sandwiched between two plates, so these droplets are going in, and they're larger than the distance between the two plates, so they're squeezed in. And if there are these dips inside, they get trapped in that. So that would be a way of a porous medium. And what we're looking at is actually a very large sample of those dips. So the small one is a millimeter, and then this square is a millimeter by millimeter that comes out of this. And you can see if you flow a lot of oil droplets into this medium, they get trapped. They get trapped in a lot of places, and they're trapped there. So they have generated thousands of droplets, and they have been flowing this into this medium, and they get stuck everywhere. It's kind of random. They have written a code to randomize the position of this pores, and then they increase their flow rate. At some larger flow rate, they're going to start moving, because now we have increased the viscous pressure from the fluid that's going in. And at the end of the day, they have observed that they create these things called the smectic rivers, which is a term that I think solid-state physicists really like it, because smectic is how the liquid crystals form. So this is an orientational order. Well, even if I hadn't done this experiment, well, they do a lot of analysis beyond that. I would have expected these to go in reverse. Once you mobilize one droplet, it's going to push on the ones in front of it. And once you have mobilized a group of droplets, they're going to start moving, and they reduce the pressure everywhere, because this is a connected system. It's hydrodynamically connected everywhere. Once you have reduced the pressure in this area, there is no point for other droplets to move. They are going to be stuck where they are, and now you have a group moving, and they mobilize each other and anybody who is in front of them. But this is interesting that they come up with a universality, so it doesn't really depend on what the flow rate is and what the pattern is underneath. So the droplets move collectively, and that's what they have found. So these experiments are hard, and it's really hard to make few droplets and then control them and study one at a time. So our goal has been to really understand the underlying physics. So I don't want to fill the medium with a lot of droplets of the same size. I want to have a system that once I can fill it with few droplets, once with a lot of droplets, once I have monodisperse, we could have polydisperse, all sides of physics of this problem. So our goal was to design an experiment that we can study the microscale dynamics. So the video you're looking at is our first attempt a long time ago with an RU student when I was a postdoc. We made a lot of droplets, and then we injected them into the porous medium. That our biggest mistake was that we stored them in a vial, and then we injected them with a syringe. And the density was slightly different. So we could then get these droplets to get out of the tube for hours. And then once we pushed them too hard, all of them went in at the same time. So we went around to figure out different methods. And that journey continued when I came to RIT, and we acquired a system that we could have tried this experiment many, many times. So we made our science much faster and more accessible. So designing a microfluidic chip is one thing. You do a CAD drawing, and then you usually send it to a company that prints it on a, forgot the English word, for photolithography, and then the pattern comes back, and then you have a wafer. You cover the surface of the wafer with a polymer that can be cured with UV. You put the pattern on top, and then you shine light. You cure some of the polymer, and then wash the rest of it away. Now you have a mold, and now you can make more of that device. So this process takes days because you send your design to a different company. We can't do that. Not everybody has that kind of facility. And then it comes back, and then you go through your soft lithography plan. Well, RIT has a nanofab facility that we could technically use, but nobody wants us there because our polymers are extremely dirty, and then they're super sticky, and they stick to everything and everywhere, and they don't really want us in there to make all of the facility covered in goo. So we acquired a microfluidic 3D printer. This happened. Fortunately, there was a gap in a lot of things. There was a year that we all went remote. And in that time, the prices went dropped on a lot of equipment, and people who had money had the opportunity to buy some equipment at that time. So, and people did some research. So I acquired a microfluidics 3D printer in 2020. And now we go from our design to printing a mold within hours. So from the moment we decide that this design is not going to work, and I wish I knew before, doesn't really work because we don't have the physics to understand this problem beforehand. So you kind of need to brute for some of these. So we made science really accessible and extremely fast for ourselves. Now we 3D print our molds, and then we make devices that are our microfluidic devices. So a few words about how we print our devices. Our 3D printer is a digital light processing printer. These printers work based on so they're not those filament that you melt them. These printers are based on fluid resins. We have a vat that's filled with the resin. There is a glass and a Teflon liner underneath. They're both transparent to UV. And we have an array of LED, well, not we, the printer has an array of LED underneath. And then when we send our design, it turns on the LEDs that need to cure the resin. So the resin is cured at 345. Is it 345? Probably. It's 345, maybe 7. And as it's cured, there's a build plate that comes down, and then the place that the LEDs shine light, and they're focused exactly on the build plate. So now it cures on the build plate, and the build plate goes up, and then it cures another layer on top. And then when this thing comes out, if it comes off, it will, your pattern is upside down, and you can take it out, wash it, and then now you have a mold. And it comes out 99.9% of the time. So when we started this work, we received a resin from the company that was selling these printers, and they were selling it for microfluidics. So each resin has a specific time for curing, so you don't burn the resin, and you need to have a specific intensity of light. So it works with the resin because different resins have different properties. These are polymers and cross-linkers that are mixed, and they cure when you shine UV on them. So the top picture is the resin we got from the company. And when we printed based on their recommended criteria, we found that we have pixelation on the surface of this microfluidic device. And we're working with things at the microscale. I cannot have a pixelation that's like 30 micron, and it will mess up my entire experiment. So I had this talented student who graduated last year from the same program as you, who decided that I'm going to do something different. And then he did a lot of research and figured out that people are using different kinds of resins. And most people are very happy with this powder, ceramic, and resin mix that is sold online on Amazon. And he purchased a bunch of them. And then we spent some time figuring out what is the right exposure and intensity of light to create a porous a surface of microfluidic device that is completely smooth. So now we went from an extremely expensive resin to an affordable resin that is almost 50 orders of magnitude cheaper, and it gives us much better quality. So after we resolve this issue, now we have porous media that has a very, very smooth surface. So none of our droplets will ever get stuck, and we're ready to do some more experiments. So we print our molds, and then we fill the molds with a polymer and cross-linker mixture. So you buy the polymer and cross-linker separately and then mix them. And then it's a Silgard 184. I'm missing a one there. And in industry, they call it PDMS. So it's polydimethyl sulfoxide something. And then you pour this into the mold and let it sit in the oven at 65 degrees for 4 to 6 hours. And then you pop this out of the mold and bond it to glass. So we don't want a device that's top open. We bond it to glass. We use plasma to activate the surface of PDMS and the surface of glass. And so PDMS becomes silanol and glass become hydroxyl, and they love each other. And as soon as you put these two, they stick to each other. Now we have a device that is sitting on a cover slip or a glass slide, which is perfect for microscopy, and it's transparent. So this is an example of what we do in the lab. Now we have designed a device that is a very nice, beautiful porous medium on right, and on the left side, we have a drop maker. So I mentioned that one of the issues in doing this experiment was that most of our systems are designed to make a lot of droplets at a very high rate, but we wanted to do an experiment that we can control. We want 100 droplets in this experiment, and we want them to go in at these intervals. And there is one regime that achieves that, and that would be a dripping regime. So it comes out of the same name as when your faucet is not really good and it keeps dripping. So in a faucet dripping, there is fluid inside the faucet. And then if you look, there is always this small curvature of fluid. But there's also gravity. Gravity pulls those droplets. As soon as you have enough of those droplets, they start falling. And then you have a surface tension. And if you don't have a very, very leaky faucet, most of those droplets are in the same range of sizes. So dripping regime is a regime that can give us droplets of the same sizes. But our microfluidics is sitting flat, so we cannot use gravity, but we can do some actual physics to figure this out. So at equilibrium, when we have this droplet that is connected to the fluid inside the inlet, we have a balance between pressure inside the droplet and the pressure outside the droplet, plus the capillary at the interface. So the capillary at the interface, which is the last pressure of the droplet, is equal to the pressure of the outside plus the capillary pressure. The capillary pressure depends on the interfacial tension between the two fluids and the radius of the droplet. So that would be 2 gamma divided by R. For this droplet to actually be detached, we need to overcome this and go out of equilibrium. So in that case, we need to create a collar of fluid that's a slight backflow to create that neck. And then as soon as the pressure in the collar is smaller than the pressure outside, it will snap the droplet. And now our droplet should have a diameter almost twice the diameter of our inlet. So this gives us very interesting physics, because first of all, as long as we have a very small flow in the fluid that is going to make our droplet, that would be our inner fluid, which means that these are coming very slowly, while the fluid outside, the outer fluid, is flowing constantly. all we need to worry about is the geometry. So if I want a droplet of 200 micron, I'm going to have to design this geometry to have something less than 100 micron. So geometry will determine the size of the droplets, the minimum size of the droplets. And if I want to do monodisperse droplets, I should be very careful to get exactly the same sizes. And it is very much possible. So we have designed a drop maker that is attached to our porous medium. So we don't have to worry about the density difference between the two fluids. Oh my God, they talked 26 minutes. And now if we have a very slow, steady flow of the inner fluid, which are our droplets, we can make these monodispersed droplets continuously in the porous medium. So this is our drop maker, and this is a movie of our data. One of the biggest challenges we always had was that this porous medium is a few millimeters or centimeters long and wide, and most microscopes just look at the millimeter by a millimeter, or maybe like 2 millimeters by 2 millimeters. So they have a very, very small field of view. So the first thing we did, we decided we're not going to work with these microscopes that are designed for biology. We are going to with microscopes that are designed for us. So we acquired a wide field Zeiss Axio, which can see very large areas. And we got the objective that has the largest field of view for us, and then attached it, which is perfect because our features are not too small. Our features are tens and hundreds of microns. So we don't need to resolve things that are at the scale of a single polymer or something like that. And now we have mounted our setup under this microscope. Our microfluidic device is under the microscope. The microscope can see the entire field. We have designed a drop maker, and we are going to keep a constant hydrostatic pressure for the inner fluid, which is our water. And whenever we want a droplet, we have a pressure pulse that's attached to the wall. So whenever the compressor goes down in Carlson, we can't make any droplet. And then we have an outer fluid that's driven by a syringe pump. Only Karen got that problem. So we have a constant flow of the outer fluid, which is an oil. And it doesn't mean anything. HFE plus FSH is the oil plus a surfactant. And if I want a droplet, I just apply a pulse. I push that button and I get one droplet out. And then if I want more droplet, I push that more time. And we didn't really get to automate this because this was just a very fun experiment. And now we have control over our droplet sizes. So I'm showing you the distribution of average diameter of two different kind of experiments. And we weren't very creative, so we call them experiment 1 and experiment 2, like thing 1 and thing 2. So in our experiment 1, we're using a single pulse and we're getting monodispersed droplets. And this is an experiment, so we have a little in the tail of the distribution. Most of our droplets are around 300 micron in diameter, and we have a very small distribution around it. In our experiment 2, we did double pulses. We wanted to create some polydispersity, and we didn't know how good it's going to come out, so we just went for it. So now we have larger droplets on average, and the diameter is more variable. So around 350 micron with 50 micron up and down in the both direction. So now we have two kinds of experiments we're going to look at. We have very good control over our droplets. In our first experiments, we took our porous media from micrographs that we cut from our confocal microscope. So we packed glass beads, 3D. We wanted to be really true to experimental standards. And then we took a slice of that, and then we put it, we printed, and that was our system. So it was very hard to flow through them because I had a filter, and our droplets were larger than our filter. So obviously they're not going to go through. So we did some modification in our system, and we decided that I'm going to have a gradient in this filter. So the top will be a little larger pores, and then as you go down, you will have a smaller pores. And that's how a filter should be, because you don't want to cake on top of your filter before you start flowing through the filter. You want your filter to absorb things and still have some flow. And you don't want the big things to go on the bottom of your filter. And you can have a still flow around them. So we used we removed some of our obstacles, pores, and we had larger pores, but we didn't do it completely randomly. We wanted the entrance to have larger pores and the outlet to have smaller pores, but we still wanted to have an average pore size that is true to some of the experiments, experimental designs that you have actual 3D bead packs. If you look at the distribution of pore sizes, obviously the entrance is larger and the end is smaller, and throughout the medium we have quite a nice and homogeneous distribution of pore sizes. Now we have a fully working experiment. So this is where we are flowing our droplets into the porous medium, and we're doing different concentration at different times. And now we have to identify each droplet. So we have gone through many generations of how to track these droplets and define them and find them. Thanks to AI, things are going much faster for us now. So our first way of analysis was, well, you binarize you subtract the background, and then we did a watershed, and then a hue transformation. So we get all these circles, and then we were able to identify every single droplet, although they were in contact. This is not really common in most of applications. When there is contact, it's very hard. That's why watershed is really needed to break up those contacts. There are many ways, different ways to do that. At some point, 6 years from now, I'm going to come back and tell you the new method. The next thing to do was tracking these droplets. So tracking in fluid experiments has been, since 2000, I would say 2, has been revolutionary. So the way people study turbulence changed once they managed to really track particles. And that was when you have multiple point of view, and then you now have a good tracking code that can predict where this droplet is going to go. The hardest thing in tracking is that things don't go at a single pace. So things are very intermittent. They go fast, and then they slow down, they turn, and they do other things that you weren't really planning. But when you put in these large droplets in a porous medium, the dynamics become extremely intermittent, and it's really hard to track them. And once you have a lot of them, most of the tracking codes, they get confused. They can't really say which one is which one. And worst thing is that they stop together, and then a few of them start moving in different directions, and you can't really have a predictive algorithm. So we had to utilize multiple techniques to really get them to be tracked nicely. So at this point, these are all tracked in MATLAB. We use a global nearest neighbor algorithm, and our filter is interacting multiple modes. So you predict what the velocity will be, what the acceleration will be, and you do that for all possible candidates. And then there is a cost matrix you need to optimize to actually get the best tracks. These are all built in to MATLAB, so it's really easy to use them all at the same time. You just need to learn how to do it properly. For each data set, we had to really have different criteria. So there was successful tracking. So every single droplet that comes into the medium, we are able to track them. And we have created this habit of putting labels on them. So we have proof that they are not being mixed, and we can track them. So tracking is really important in fluid, because once you measure velocity and acceleration, you can really define forces. And that's what we want as physicists. We want to know what the forces are. There were some interesting things about these emulsions. So when we started these experiments, my naive prediction was that the first droplets are going to go through, and then when we have a lot of droplets, they're going to get stuck, and then we have now a filter that is completely stuck. When we started doing the experiments, especially at low concentrations, we found that the first few droplets, they're going to go and they're going to get stuck. So they're not going to go through because droplets are not really smart. They can't see multiple pores in front of them. What they do is that the only thing they feel is the velocity gradient on them. Wherever there is a large velocity gradient, they're going to accelerate and then follow that streamline. So obviously, the largest velocity gradients are when you go from through a small pore. So things are really, they're pushing you through and then you go get stuck. So if you're in a crowd, don't go through the largest velocity gradient. Find a different path. So droplets go through and then they get stuck. And then the next one comes and so these droplets are spheres between two plates. There is flow around them. There is still flow around them. So they can't really see that. And then more of them come and get stuck. And now you have a lot of them stuck right in the middle. And none of them got through. And then this population keeps increasing, and you have some areas that you have a lot of clogging, and some areas that they start moving. And then the areas that are clogged, they're clogged, so no more droplets is going to get to them. And then the other droplets find paths along the velocity gradient. So contrary to what I predicted, we actually have trap, clog. We modify the space first, and then the droplets start percolating through. So at the beginning, we have very little percolation. So if I take the porous media out and I keep looking at how the droplets, so the movie up there is showing us how the droplets are going through. And as you see, we have different pulses of fluids. So this the distribution on the left and bottom, they show us how many pixels are being occupied. And this is a pressure measurement along it. So unfortunately, the axis of the pressure goes up and down. So it's kind of hard to tell. But as you can see, the medium is now being filled with droplets. But we continue to have percolation through the medium from different paths. And this is very, very unique to this porous media because when we repeat the experiments, we get this same dynamics. One of the interesting dynamics is always when you compare your large droplets to tracers, that would be the fluid elements. So that was a separate experiment that we had these fluorescent tracer particles that are 10 micron, they're going through and they don't get stuck anywhere. So when we look at the distribution of velocities of droplet and compare them with tracers on a log normal scale, we see that the tracers mostly are flowing around the interstitial velocity. The interstitial velocity is the average velocity you expect for the medium. Although the velocity is very different everywhere, you have a constant flow rate and you have a geometry that's slowing the flow down, but you have an average velocity you can define. So the tracers, the black ones, are around that velocity, and they have very large, a very large population have very small velocities, and 10 to power minus 3 of that population, so thousands of them go twice that velocity. But when you have droplets, they have a very different dynamic. So both the monodisperse and the polydisperse experiments, they show that a much larger population of droplets tend to have very large velocities compared to tracers. Although the droplets go slower than the tracers on average because they're larger. And it also depends on how the medium is evolving. So the plot on the right showing us three different timestamps. So the first, and we're looking only at the first 100 monodispersed droplets. So the first 2 seconds of the experiment, our distribution shows that most of these droplets travel 1 millimeter. But as we go further throughout the experiment, we have a lot of the droplet flowing, going at shorter distances, and suddenly we have a peak of some of the droplets that actually traverse through the entire experiment, while a lot of them has stayed in a very, very small distance that they have traveled. So it means that a lot of them within 10 seconds end up being trapped in the medium. So comparing the x and y velocities, so the x velocity is the longitudinal component. We still have a larger distribution. The interesting thing about the y velocity is that we have more on the both sides. So the droplets, instead of going forward, they have a lot distribution on going to both sides. Also on the x velocity, we have a significant amount of backflow. So the droplets that are going this way, they start moving up and down, and then they flow out of the system. I'm going to take a break. So the big difference in droplets versus particles is that particles always go through. But the droplets get stuck. So the Euclidean distance that they will travel will be different for the ones that are being trapped. So this graph is a little handful. I'm going to explain all of this. You're looking at two different experiments, monodisperse and polydisperse. So the crosses are monodisperse and the circles are polydisperse. Also, we're looking at what the velocity of the droplets are as a function of their residence time, the time they have spent inside the medium. We're looking at the average velocity of a single droplet. And I'm going to color these based on the distance that they have traveled. If they have gone through the entire medium and they've made it all the way to 14 millimeters, their color will be lighter. And if they're still traveling a few millimeter, 1 or 2 millimeter, they're going to be black in this graph. And then because we have a lot of droplets, I can't put all of them here. So we have pinned them into groups. And the largest symbols show that there are 400 droplets that they have this dynamic. And then if we have one droplet, around like 1 to 10 droplet having a dynamic, that kind of dynamic, it's going to be the smallest symbol. So I'm looking at the average velocity as a function of time. What would be a velocity as a function of time for something that has a constant velocity? So you would have a 1 over time slope. And then that would be your you get your velocity. Velocity scales with 1 over time because velocity is distance over time. And so you would have a 1 over time slope here. And if I had droplets that they were all just traveling, we had all of them on the same line. And we could have get our distance from that because the acceleration is going to be 0 here. There is acceleration here. Sorry, that was a mistake on my side. But since these droplets are being trapped, some of them they have a very long residence time. So on the x-axis, they are all the way out there, but their Euclidean distance is very small. So they haven't made it through. If I'm going to take all the ones that are trapped, now because we have a measurement of the distance they have traveled, you can take all the ones that are trapped. That's the other slide. And put them and take them out of our plot and put all we have for the ones that have gone through the entire medium. We get two populations of droplets. So the velocity of these droplets, the average velocity of droplets, depends on the residence time of the droplets in the medium. And it's a 1 over time distribution. But they're in two different plots. So they have a slightly different intercept. When we went back and looked at our data, we found that our medium ended up having only 2 percolating paths at the end of the experiment. And if I color the ones that go from the top path versus the ones that go from the bottom path, we find that since they have the same path of going through, they actually segregate to 2 groups, and the color represents if they're going from the top path or the bottom path. So this was very anomalous. why would this happen? Because we have a system that is supposed to be very, very random. When you have a distribution of pores and you're moving things along, why would they end up on the same path all the time? So this was where we decided that we have designed an experiment that kind of fell into that minimum of the energy for everything. So we have designed an experiment that has mostly monodispersed droplets. The size of these droplets are slightly larger than the smallest pores. And our porous medium has this gradient in the distribution of pore sizes, and we have used the same porous medium for our experiments. So we decided that to get out of this minimum, we need to perturb the system. So this was a design choice we had done in our first experiment, and then we fell in this minimum, and now we're stuck in this minimum. So by introducing polydispersed droplets, so now we have changed the size of the droplets. They're slightly larger and they're not the same size. We ended up segregating these two paths slightly, but we're still on the same two paths. And the reason for that is that if you see there are some in between the two lines, and those are the ones that they switch paths. Those are the droplets that they end up switching paths. So obviously, the geometry was very important. And if you study porous media, they always ask you this first question: why do you use this geometry? And is it universal or not? Does it represent all porous media or not? And obviously, this particular one did not do that. So this next thing to do was really change the porosity of the medium and the geometry of the medium. At this point, we decided to increase and decrease the porosity. We know what happens if we increase the porosity. If you have more space, you're going to approach a channel eventually. And also, we decided to look at the width of the medium. So if we have a wide medium versus a narrow medium at a 50% porosity, which was similar to the beginning. And we're looking at the overlay of all the droplets going through the medium after a very long experiment. And we're still doing monodispersed droplets. So for the 40% porosity, a short and a long medium, we have created only a few paths. The short one is actually a part of the long one, so it's just a different print. But the same dynamics, the same geometry at the beginning. The 60% porosity, we had a lot more paths. Wide and narrow are one of the most are some of the most interesting ones. So by just increasing the porosity to 60%, we have mixed these paths. So now we have all of these droplets going through switching paths and going through different paths. Our 40% porosity actually became tighter because we ended up on very, very similar two paths that are very close to each other. I'm going to skip this. The next thing we decided was to look at, we never changed our droplets deformability. So we decided to let the droplets deform significantly by adding a surfactant inside the droplets and let them deform throughout the medium. So now technically we have looked at all the different parameters. We have changed our geometry and we have changed our droplets. So for soft droplets, which is the bottom plot, versus the ones that get stuck, the non-deformable droplets, we see that the soft droplets, they start moving, squeezing through the pores, and this is a more dynamic system. As we go forward, we have more droplets squeezing, and also if you have enough pressure, you will end up opening some of the paths. If we look at the distribution of velocities, this was the thing that we looked at a few minutes ago, and the more you have in the tail means that the more intermittent dynamic and faster dynamics you have. As we increase change the porosity, especially when we increase the porosity, we increase the width of the medium, and we decrease the interfacial tension, which means that the droplets are more deformable. They start to have more rare events, and now they are not that rare because the distribution starts going up. Now we have most of them, a lot of them going to, with the average velocity, but a lot more start to take larger and larger velocities. So we have events of bursts a lot more often if we have a wider porous media, if we increase the porosity of the medium, and also make our droplets softer. So the bursts start happening if we have all of these criteria. And if you compare it to a filter with small pores, and if you're flowing very, very hard material to that, it's going to clog faster, and then you have much smaller distribution of velocities of material going through that. So I think I'm at the end of my time. How much time do I have? Oh, okay. I can go all the way to the, okay. So I'm going to skip that one. That was the same message. One of the hallmarks of transport through porous media is anomaly. So if we have tracer particles or fluid elements going through a porous medium, it has they exhibit a super diffusive transport. What does it mean? That well, what kind of material have super diffusive transport? So you all kind of know what is a diffusion transport. It's a random walk. You just go around and then you kind of diffuse it. But if you have in reflective surfaces or a boundary on top, that would be a lot of like topological materials, they start to have super diffusive transport of electrons, because now you have introduced a way of bouncing in your system. And over 10 years ago, a group decided to really look at what happens inside porous media, because there was never a description of transport inside porous media. So they figured out that a fluid element has a mean square displacement that has an exponent larger than 1/2, and that would be a super diffusive system. So a diffusive system is that when you measure the mean square displacement of this particle just bouncing around for itself, and it scales with time to the power of 1/2. But as soon as your exponent gets larger, and specifically larger than 1, you have a super diffusive dynamic. So for droplets, we were not really sure what kind of dynamics they're going to have, because these are large, they're not fluid elements, and they have a lot of intermittent dynamics. So if we measure, and this is for 2 of our data sets, our 60% and 40% porosity, so our largest and smallest porosity, means that the ones that went through very easily compared to the ones that got stuck mostly. If we measure the mean square displacement as a function of time, and I'm going to display it on log, so the scaling is very easy to see. If it was a diffusion, we would have a scaling of time to the power 1. This is not this. This is the mean square displacement. And if I have a super diffusive, I'm going to have an exponent that has a larger power. And if I have a subdiffusive transport, I would have an exponent that would be much smaller than 1. So for droplets at short time scale, we see that they have a super diffusive dynamic, which means that at short time scales, they just behave like tracer particles. So they just behave like the fluid around them. But at some intermediate time scale, they start to approach a diffusion. So it means that they go, stop, and then move. And then at very long time scale, they start to show some subdiffusive dynamics, which I cannot really explain why. My suspicion is that this is now dominated by the ones that actually don't move at all. So the data would be biased. So I need to remove those, figure out which ones are not moving at all, and then remove them from this data. But the interesting thing is that at an intermediate time scale, we start to have a diffusive dynamic. So the droplets actually start feeling the medium as opposed to tracer particles that do not really feel that, and they keep bouncing around. So in conclusion, transport in porous media is really dominated by the geometry. Most of the work was done by my PhD student, Michael. So this is our picture when he graduated just a year ago. He was my first PhD student, and he was from imaging science. And now we are looking at more interesting dynamics of deformable particles, so gels, with my most recent PhD student from imaging again. So the bottom picture is my current group. So Jason is in imaging, he's in front row. And this work was initially supported by the American Chemical Society and now by the National Science Foundation. Thank you. Do we ask Zoom question? Oh, Jason, you have a question?
So, you have two categories. One is oil recovery in rocks, and the other is in like the food and the pollution industry with the filters. The setups you have for your experiment, like you said, you have larger pores to start, so that the bigger things can go into the porous medium and get stuck instead of sitting in front. Because you now have that spatial pore size gradient going along, would that actually affect some of the dynamics and change some of the results you find between the filtration stuff and also rock recovery or oil recovery in rocks?
So the heterogeneity in pore size distribution is something in rocks you cannot control. And it is very common that some areas have large pore size distribution and suddenly you change medium and now you're in a different regime. So having heterogeneity in general is good. Should we have created a medium that has alternative porosity? It would have been nice. So we specifically designed everything in this system that if you divide it into different sections, you always get the same porosity. This is like you're deep in one section of the medium. When it comes to filters, they actually design filters layer by layer. Or if you want to have filtration somewhere, you better have different filters. So your 0.1 micron filter is the last one that's going to capture. And then your 20 micron filter is the first one. So it's more relevant in the filter, the way we have done this experiment rather than rocks. And dynamics, we are all working towards finding a system that can be scaled up. This is what the industry actually wants, both oil industry and other industries like chemical processing. They want to have statistics on a certain dimension of the system that they can predict what would happen if you repeat this many times. So you do it on a unit cell and then you repeat it on larger scales. Yes.
I understand why you don't want to do this theoretically, because there's so many parameters of the system. There's different kinds of viscosity, right? The compliance, the surface properties are probably very complicated. But how much control do you have, or what do you try to do? Do you functionalize your surfaces? Do you put surfactants for your liquids? And what are you trying to do to kind of reach a sweet spot?
So all of experiments are water and oil droplet, and the oil loves so the oil is hydrophobic and the medium is hydrophobic. And droplet is is in the middle, which is exactly the same as oil, because most of the rocks love water and they hate oil. So it's the same, just the fluids are switched. If we could pattern the contact angle throughout our medium, that would have been great. So we would have some areas that had hydrophobicity, some area were hydrophilic. We don't have that ability yet. For Fluids, yes, we do. We modify the surface tension a lot. So we both have surfactant in the oil and water, and we vary the concentration, and we have looked at different surface tension throughout the medium. I do not expect that the physics will be very different if we have a hydrophilic medium, because then you switch the phases and now your inner fluid become your outer fluid. So that would be an entirely different problem from what we're doing.
Your medium, your template, you functionalize that at all?
With aquapan, yes, to make it extremely hydrophobic. Yes.
So,
Yeah.
so this is like the natural convection regime, of course.
Advection. So yes, there is a constant flow that is an advection term, but not solvable, still not solvable numerically. Well, because of the interfacial tension between the fluids, it's almost impossible to have a mesh that resolves all the interfaces at all time. We can, we have collaborators that they do a few droplets at a time, and they still can do it, but not at this concentration.